Hello everyone and welcome to my channel. In this video I would like to show you how to program a low-cost FPGA board, the Tang Nano 20K, in both Verilog and VHDL. For that I'll be using open source tools under FreeBSD. Okay, let's do this. This time I'll be using two different machines, one where I'll be installing the tools and another one where I will be developing the code in Verilog and VHDL and programming the board. I could use the same machine, but since I've installed already the tools, I wanted to have a clean machine to show you how to do everything from scratch. So here you see that I'm under the machine, the Yoga 370, which is a laptop that I own, and I'm going to change to root, and now I'm going to search the YOSys, which is a synthesis tool, and here we see that we have the YOSys Open Synthesis Suite and the plugin that we are going to be using. We can just install these ones in YOSys and the YOSys GHDL plugin. Alright, another tool that we're going to be needing is the ABC tool. Let's see, ABC, sequential synthesis. Okay, so pkg install ABC. Next, we're going to need the next PNR for place and route, which is already present in FreeBSD. However, we require a special version for the Tang Nano 20K, which is unfortunately not yet available in the ports tree. So we're going to have to compile this by ourselves. I hope to contribute this improvement to the port in the future. For now, I'm just going to create a directory, temp, and a git clone on the next PNR tool. Now we go to the next PNR. And we create a build directory. We go to the build and issue the following command. Now we see that we're missing the eigen3, and let's search for this. So we see that it's available under eigen, which is version 3.4, so let's install that. Now we try again to compile, so we issue the command cmake, and let's try to compile with 8 threads. We see again that it's missing the boost program options, so we pkg install boost. Okay, pkg search boost, pkg install boost, and let's go for all. Probably the boost-libs would have been enough, but yeah, let's just install the -all. Let's try again, make J8. So we are again having some problems. Let me just show again. So if I try to compile, I get the same thing. But if I look at pkg info -l boost libs, and if I try to search for the program options, so sorry, need a grep here. We see that this is available in the under /user local include boost. I could search for the flag for cmake to make it happy, but I'm just going to do a really bad thing, which is going, because I'm running as root, user include link the boost library here. So link s here and cd boost, it's there. So let's go again to the temp and let's try again, make -J8. And now we can see that it goes. The next problem we're going to find is that we need the apicula which is a Python library. So let's see, we don't have pip, pkg install pip, py311 in this case, pip, and pip install apicula. And let's try to compile again, make J8. Alright, so it compiled now, and the next step we would just type in make install. And you can see it has installed the next PNR Himbashel, which we are going to need afterwards. So just that you can see, the apicula we installed before actually installed the GoWin pack. So yeah, it's to pack the bitstream for GoWin FPGAs. We are also going to need this. Next, we can install a small program to run a test bench and to investigate the waveform output. So this is called GTK Wave. We can also install it. Another tool we're going to be needing is the Open FPGA loader to load things to the FPGA. So pkg install Open FPGA loader, and in this case it was already installed, so yeah, it's fine. And that's it, we have the entire toolchain installed. Now I'm going to switch to my other machine where I have the example already prepared, and we are going to see how to compile Verilog and VHDL to a bitstream and how to transfer it to the FPGA. So now I'm in another machine where I have the examples prepared, and we are going to start with the example for Verilog. So as you can see here, I have a makefile, blinky.cst and blinky.v. So let's start with the Verilog file, which is pretty simple. Just defines a module blinky to blink an LED. It has an input, the clock input, and an output, the LED. The clock is going to be running at 27 MHz, and this means that if we are going to turn on and off the LED at a speed of 27 million times per second, we are not going to see the LED blinking. So for that, I create a counter, and always when there is a transition in the clock, I increment the counter. So it's going to count in binary 0, 1, 2, 3, 4, etc. And the LED is going to be at the output at position of the counter bit 24, because it starts at 0, so it's yeah, the 24th bit. This effectively means that the speed at which it's going to be toggling, it's going to be 27 MHz divided by 2 to the power of 24, and that is about 1.6 seconds. So the LED is going to be blinking at a rate of about 2 seconds. Alright, so now let's look at the makefile. And the makefile says that the first rule is we want to build everything, and everything is blinky.fs. And we go here down, the blinky.fs depends on output.json. Output.json depends on blinky.json, and blinky.json depends on blinky.v, the Verilog file. So let's read from top to bottom. From the Verilog file, we produce a synthesized version, which is called the JSON, the blinky.json, and we do this with the YOCs and the parameter -p, read Verilog, read the blinky.v, and synthesize for the GoWin FPGA, giving the output on the blinky.json. The blinky.json file that gets produced is now going to be run against the next PNR to do the place and route on the FPGA. So we take the input blinky.json and we write as an output the output.json. Here we select the device, which is the device required for the Tang Nano 20K, and the family. And here, very important, we say --vopt cst equals blinky.cst. what is this? Let's open the file, blinky.cst. It tells us in the Verilog file, the clock signal goes to pin number 4 and the LED goes to pin number 15. Well, you need to look at the specifications of the Tang Nano to see the clocks and to see the pinout. In this case, I can tell you that pin number 4 has a clock of 27 MHz. This is a fixed clock, and one of the LEDs available in the board is available in pin number 15. Here we get an additional configuration for the port on the clock. It's an CMOS 3.3 volts. The pull mode is none, and we also get the bank VCC I/O to 3.3 volts. Something very similar for the LED, just that we write drive equals 8. Alright, so we need that file for the place and route, because the place and route needs to know where to route the signals. Once we get output.json, we are ready to create a bitstream to be uploaded to the FPGA. And this is the blinky.fs. That is the file that we're going to use together with OpenFPGA Loader to load the project into the FPGA. For that, we run go-in-pack on this device, output blinky.fs, the bitstream, and we take the output of the compiled project. That's it, very simple. Here I just give some rules in case we want to clean the project, we get everything back from start. So let's exit and let's just type in make and see some magic happen. Okay, so I'm not going to go into the details of what just happened here, but the important thing is to see that we have a file, the blinky.fs. And this is going to be the file that I'm going to program in the FPGA. Now, let me just show you very quickly that when you plug this device into the USB port, it basically just does some nice pattern with the LEDs. Let's have a look at this. So here we have the pattern going here. So in this direction here, it's just going like this. I hope you can see. It's not very optimal, but you are going to you are able to see this. Now I'm just this project is just going to blink one of the LEDs. So let's change to root and home. We have here the blinky.fs and now USB config, and we see here that the device is plugged in, is the UGen04, and let's just run OpenFPGA Loader -p Tang Nano 20K, and we give it the blinky.fs. And now let's see, I'll put the thing here in, and I'm going to press, okay, and let me just press enter. Now you see the LED disappeared, so stopped blinking, and it's programming the new one, and let's go. And now we have the LED just blinking at about the rate of switching on and off at about every 2 seconds. All right, so that's it for the Verilog part. Now let's try to do the same with VHDL. For that, I'm going to go to the VHDL directory, just in case I've done something. I'm going to look here. Here is a slight different thing. You see one more file. This is a TB, a test bench. I'm going to show you this in soon, but let's focus on these 3 files. So blinky.vhd. It's basically the same project, and written instead of in Verilog, it's written in VHDL. Here we define an entity blinking, which has a port, the clock, which is an input standard logic, and the output standard logic, which is the LED. We define the behavioral architecture of Blinky. as between the begin and end. For the synthesis, we say that there is a counter which is unsigned 24 down to 0, so it's a little bit larger than the Verilog. We say this is not really interesting for hardware, but we say that when some simulation starts, it starts by assuming everything is set to 0. And we have a process in the clock. So if there is a rising edge on the clock, it changes from 0 to 1, the counter increases, and here the LED is assigned to the bit 22 of the counter. If you remember, previously I assigned it to bit 24, if I'm not mistaken, and now I'm putting it a little bit lower, meaning that it's going to be blinking a little bit faster, about 4 times faster. So in the blinky.cst, we basically have the same content, so nothing new here. Where something is changing is in the make file. So let's have a look. Again, to build everything, I want the blinky.fs at the end. Blinky.fs depends on the output JSON from blinky.json, blinky.json from the work CF. Now this is VHDL specific. And the work.cf depends on the VHD file. To produce the work.-object93cf, I need to do an analysis with the GHDL, which we installed before. So this is this step here. And once we have this, we can generate the blinky.json. In this case, and I think we actually don't need to put the full path here, so let me just take this one out and let's try it out like that. We just say YOCs using the module GHDL, which we installed also previously, which was the GHDL plugin. And now in the -p, we do the same thing, the synthesis for GoWin, but instead of reading from Verilog, we just call GHDL, which is going to read and load the current work. Then the next steps are basically the same, because we produced a blinky.json and we just produced the output.json in the same way, the blinky.fs also in the same way, and we are ready to rock and roll. So let's go back here. VHDL, and let's compile. And we have again produced a blinky.fs. Now let's try to load this. So su, and the LED is it's still blinking at the same rhythm. Now let's just try to load this with a new blinky.fs. And if you remember, what happened is that it should be blinking faster. So let's see if this happens. Let's run this. So it stopped blinking and it's loading the static RAM. And almost there, and there we go. Now, as you can see, it's blinking much faster. Okay, so this is the how to get the project in. And I said that there is a TPE, a test bench here, starting a new terminal, so V and VHDL, and there we are. So, and now I'm going to do a GHDL. Actually, before that, I'm going to look at the TBE here. The test bench is like this. The test bench is used to test our design. So it's very similar to the previous one. We have the use statements. The entity has no signals to expose. It just runs by itself. There is the architecture simulation for the TBE. The TB Blinky. This internally has a signal, the clock set to 0, the LED, which is initially set to undefined. I defined a clock period of 1 nanoseconds for a 1 gigahertz clock. Notice this is a simulation, it's just to, it doesn't really matter here. The device and the test is the entity, the Blinky, where I'm mapping the port. So I'm putting the internal, the exposed clock from the Blinky. I'm connecting it to our signal, which is also called CLK. And the exposed signal LED on the port is also connected to the our test bench LED. Now there is a clock process, and here we just go and switch the clock from 0 to 1 at half the clock period to make it 1 gigahertz. We do this as long as the current time is less than 100 milliseconds. And that's it. Nothing much more to say about the Blinky. Now we should analyze everything. So GHDL-A, Blinky.VHD and TB Blinky VHD. It analyzes without problems. Now let's elaborate GHDL, elaborate the TB Blinky. Here we don't need the -VHD, so we elaborate it. And now we can just run the TB Blinky. We output a VCD to the Blinky.VCD. This is the recording of our signals that we're going to be examining afterwards. And let's stop the simulation at 10 milliseconds. So there it is, simulating. All right, so it stopped at 10 milliseconds. It does take a little bit of time because this is simulating hardware. And now we can see how, what are the results of the simulation. For that, I can use GTK wave, and load the Blinky VCD. So let's expand here. We see here that there is the test bench Blinky. Inside we have our device under test. In the test bench Blinky, we have defined the clock and the LED. Inside of the device under test, there is the clock, the counter, and the LED. So actually, I want to see the things inside the device under test. So I just drag here the clock. It does take a little bit of time. The counter also takes a little bit of time. And the LED. You see here it starts with undefined. Now we have 1 femtosecond, 2 femtoseconds. It's really very time. The time scale is really not set correctly. So we should start zooming out a little bit. Let's go. And at some point in time, we should see that the signal, we start getting some transitions at 500 picoseconds, which is half a nanosecond. We transition from 0 to 1, and the LED now is it goes to 0 because it's assigned to the bit here, so the simulation just sets it correctly. So, and now it goes increasing 4, 5, etc. And we can continue zooming here, zooming out, and you can see the clock goes and goes and goes, and we don't see any transition in the LED. Why? Because the bit is actually quite high. It has to count a couple millions until it flips the LED. So let's do a fit zoom, and now you can see. So don't forget, I'm simulating at the clock at 1 gigahertz. The clock in the FPGA that I just shown was 27 megahertz, quite much lower. So the time here doesn't match what we saw in practice, but it shows you that the clock has to change way too many times for us to observe a change in the LED. And this, with the GTK wave here, we can just confirm that our design is actually doing what we are expecting. That's it for today. I hope you liked the video, if you did it. So if you liked it, please give it a thumbs up. And if you have some comments or suggestions, please use the space down below. Please forgive me if I cannot, there are some comments that I've received previously, and if I cannot react so fast, it's because currently I'm relatively busy. but I will try to get and to work on some of the comments because they are really interesting and good ideas there. So thanks a lot for all the comments. Thanks also for passing by, and yeah, take care. See you next time. Bye bye.